So today we're going to start a new topic for SR motor. That's also the last topic we're going to discuss. So SR motor is one of the most important motor I think will be in the market here. Key thing is SR motor do have a lot of advantage as compared to other conventional motor like DC motor and also brushless DC motor or induction motor. You see other motor are based on the conventional principle by using so-called the Lorentz force, which interaction between the current passed through a conductor plus the magnetic field will create the Lorentz force or the Lenz laws. And this is quite conventional. However, this do impose a method. We do need to have some kind of the magnetic field appear in the circuitry, existing magnetic field. So the magnetic field can be generated from PM permanent magnet or a kind of the field circuitry. Like DC motor, we have a field circuit. And also like induction motor, we need to have the stator to create the rotating magnetic flux. So in a way that can be somehow create a lot of design problem and also a lot of the complication. So, and then there's a lot of other issue for motor, as conventional motor. Like DC motor, we do need to commutator and carbon brushes. And for induction motor, we need to have the motor which are under the asynchronous. So that means the control of motor speed may not be so wonderful. We usually cannot control the motor speed really well. And another big issue will be fault tolerance. For all the motor we have been studying, if any one of the wire is broken, the motor is not working at all. No way you can able to continue to work, not able to control torque, and not even able to rotate. So that means for the fault tolerance point of view, we have problem. All this motor we are now using is a big issue too. And then for the high speed, so could you tell me or estimate which motor you think will be highest speed, the top speed, the best speed of the motor? Induction motor is high speed because it's contactless, right? How about Ali? What do you think? Okay, it's a good guess. Usually, a high-speed motor must be without any contact between the external circuitry and the internal circuitry. So in theory, you may think induction motor because the contactless is one of the best. Of course, some people may think it's brushless DC motor, also contactless. But you can see that all these two motor, the induction motor, we got winding. So that could impose the inertia in the rotor may not be too light. And also you can see that for the brushless DC motor, we got the PM in the rotor. You're also making the rotor quite tedious and also quite heavy, higher inertia. In fact, the highest speed motor in the world, as far as I know, is the switch reluctance motor, SR motor. So that's later on, I'll tell you why. That basically this motor, we don't have anything in the rotor. The rotor circuitry is really, really simple. No connection, no winding, no PM, no inertia, no cost too. So that's why I'm making this motor become the highest speed of the motor in the whole world. And of course, fault tolerance is one of the major advantage for this motor too. And then because of fault tolerance, you can see that this SR motor, we're going to have really high reliability, really reliable, because we have very little component, not complicated design, and also even though a few windings broken, the motor still work. So later on, I'll show you why it's like that. And key thing is, as I say, is really simple structure. You can see the DC motor. We've got the armature circuitry. We also have the field circuitry. In this motor, we got stator circuitry, and the rotor, we also have the rotor bar and also the rotor circuitry. Actually, the configuration for all this motor are quite complicated. Even though when we examine the freeway, I think the induction motor freeway is quite a lot of the freeway there. So that's why it's quite complicated. And another issue we look in the motor will be the manufacturing potential. You can see the DC motor, induction motor, the manufacturing is quite complicated. A lot of the component assembly work. You can see that if we like to assemble a brushless DC motor, we need to stick the PM on the rotor, on the rotor shaft. So that creates a problem. We see that many PM motor do have problem when we stick the PM onto either stator or rotor. Because firstly, the arm blower is the main component we make for the PM. They are actually quite brittle. So when we use our PM, probably when it drop on the ground, it break into pieces. So that's why this kind of motor is not really, the PM is not really reliable. How do we stick the PM into the rotor stator? Many cases we use glue, super glue or something to stick them. So that means after a while, they may become fragile. Sometimes we need a kind of the mechanical matching to match the PM on the stator rotor. But anyway, it's really difficult to fix them properly because they're two different materials to fix them. Sometimes we have problem after use for a long time, 1 year, 2 years, the positioning may be changed. The glue may be changed. Even though we use some mechanical fixing, that may be vary too. So that's why the reliability for the fixing for the PM also become a problem too. So that's why initially the PM machine and also industrial machine could be really expensive in manufacturing. However, they've been in the market for more than 100 years. So that's why the manufacturing really mature. So that's why they have really low cost of manufacturing. But however, later on when we see the SR motor is really simple. So in theory, their manufacturing process will be really simple and straightforward. So in the future, if we really involve the SRM manufacturing, the cost will be much lower because it's simple and less material, everything will be straightforward. So that's why I think SR motor do have a potential against all the other motor you have learned in the past. Anyway, so today we're going to discuss about this SR motor. We involve the principle in here. There's an inductor in the motor. We need to discuss about that. That's a key thing for us to develop the torque. And then we also examine the torque equation and the phase relationship between the stator and the rotor too. And then for next section, we're going to discuss all the other things like the voltage equation, the thrust, the motor driver, and also the key feature of the motor and application. So that's a very interesting topic. We also see that for SR motor, you see all the universities should have a course in motor, electrical machine or motor. But since they seldom in the undergraduate spend too much time on the SR motor, I think, do you know why is that? One thing we see the SR motor has been invented earlier than DC motor and earlier than industrial motor. Some people told me they invented more than 200 years ago, right? One of the earliest motor. However, I can see that still not a really nice big market share. The biggest market share must be DC motor and the industrial motor. The industrial motor only very small market share, but it's so good. Anybody can tell me why is that? Why nobody care about the SR motor?
You mentioned it is simple in structure and everything.
Everything is good. You can see what I discussed just now.
Yeah.
Everything is good, but nobody care. Nobody try to manufacture in mass production, right? So strange, right? I think the key reason is SR motor, we have to use power electronic to drive them. Without power electronic, it's no way you can work. You see for DC motor, conventionally, we can just using DC, the motor can work. We don't need any power electronic. So that means even though 50 years ago, when we don't have power electronic, DC motor was really mature. You see the first few electric vehicles in the world, 100 years ago, is also using DC motor. And then for industrial motor, electrically, we can use AC to drive the industrial motor without any power electronic inverter. So electrically can drive them. So that's why for these two motor, since we can naturally to drive by natural source, power source, so that's why it has been very mature. So since 100 years ago, when these two machines are developed, many work has been done. So that's why it become mass production. Since they have been mass production, the cost will be really, really low, even though how complicated they are, they're still under the mass production. But for SR motor, because we only need power electronics to drive them, The power electronic developed 50 years ago, but become more mature, more buffered about 30 years ago. And then since then, we have a lot of the work being done on SR motor since 30 years ago when we had SR drive. But still that development is quite slow because the DC motor and industrial motor dominate the market. So making the SR motor really expensive because the manufacturing facility is not tailored for the SR motor. Still very expensive. The total market share, I think, just a few percent. So that makes the SR motor have a lot of the issue. So today we're going to show you how good they are, what's the key principle, and then you can therefore understand this beauty of the motor. So anyway, so we can see that SR motor is something quite different from industrial motor. Firstly, talking about rotating magnetic flux. You know the industrial motor is based on the rotating magnetic flux to introduce the flux linkage to the rotor winding. And then for the DC motor, we do have the DC magnetic flux coming out from the field circuitry. So this is two major things for the conventional two motor. But for our special motor, we're talking about SR motor here. As we call it SRM, series reluctance motor. It does not depend on these two. We don't need these two to do that. So actually, when the motor is stationary, there's a low magnetic flux. You can measure. That's something quite nice. The thing is, when like this motor, if putting a motor on the ground or anywhere, you can really use some sensor detect the PM inside the motor, which you can see that if this motor using in some security purpose or some highly dedicated system, then you can detect its existence. So that means for some kind of the safety, security, we don't like to use those PM motor. For industrial motor too, we got with rotating magnetic flux. So that means the kind of magnetic flux involved in the motor also quite a lot. So that means you can able to detect the rotating magnetic flux quite easily by using other sensor. So if you want to have a highly secure motor without any detection by other sensor or in security purpose, we should use this SR motor because this SR motor does not depend on any rotating magnetic flux or DC flux. But of course, other motor do have other more problem. Like this motor, the weakness of a motor will be commutator and carbon brushes. Like synchronous industrial motor, we do have this like the asynchronous DC motor, and we also have the slip ring like those round motor, industrial motor. But for our SR motor talking about here, we don't have that issue. So that's why this motor becomes so marvelous. That's what I think. As I mentioned before, this motor can only develop with the power electronic. Without power electronic, it doesn't work. So make the mass manufacturing major development become so slow. So this motor also called the variable reluctance motor because we use so-called the reluctance principle. I think you know reluctance because when we're working on transformer, we know reluctance circuitry. So reluctance will be something we're going to stop the magnetic flux go through a magnetic circuitry or reduce its capability. But however, we can make use of that reluctance in order to move the rotor to rotate, or even for linear motor, we can also move it. So the principle here will be try to vary the reluctance. So we create a reluctant force. So later on, we'll show you what kind of reluctant force. So that to say we are able to create a reluctant force by returning on the stator, create a reluctance between the stator. So that's a principle that if we are able to minimize the reluctance, that's usually all the magnetic circuitry will be automatic flux. We'll try to go through the lowest reluctant path. Of course, just like current, the current will tend to go to lowest resistance path. So that is to say when you have a number of parallel resistor, more current will go to low resistance. For magnetic circuit as well, the magnetic flux will try to go to lowest reluctance. So by using this principle, we can therefore create a force component. So you can see that configuration for stator rotor are quite simple. From this diagram, you can see that the stator just a piece of the metal with this kind of salient pole. We can put the winding on here. And for the rotor, we do have some salient pole here that will help us to complete the magnetic circuitry. So the good thing is that there won't be any weak linkage like this motor. We don't need to use commutator and common brushes. There's no slip ring. And because we do have the magnetic flux pass through them, when we energize the winding here, we do have magnetic flux to pass through them. So this magnetic flux may also pass through the stator and the rotor. So that's why we still need to put a lot of lamination. The lamination layer will be put in like this. So this is to say we can stop any eddy current. You see the eddy current, when we have magnetic flux like that, the eddy current tend to go to this way. So if we do a lamination in such a way that this eddy current we're not able to pass through, then we can stop all the eddy current losses. So that remember, eddy current, we should do it in such a way. So next diagram, we can see how the configuration look like. So this is one of the simple SR motor. So of course, they're so simple, probably we seldom use this kind of too simple structure. We tend to have a more number of poles. So in here, the stator. Yeah. So the stator, we are winding in such a way. You can see that once we do the winding, then in theory, the magnetic flux will therefore complete the loop in here. Be able to complete the loop, depending on the direction, the will be like that. So the magnetic flux will pass through this air gap. Yeah. So that is to say, if the air gap is not large enough or the rotor have a way we can let it to free rotate, the rotor will rotate until the air gap here becomes less. Or in this case, we can able to reduce the reluctance for the whole magnetic path. So that's the principle here. The reluctance here will try to minimize in this magnetic circuitry to allow all the magnetic flux to go through this air gap. To go through it, then we need to the system will rotate is by itself until we narrow the gap. So later on, I'll show you the inductance principle, then you can know more about it. So basically, if this thing is not aligned like that, is aligned in here, then you try to rotate until we narrow all the gap between them. So that's the principle behind. So you can see that in here, we are not using Lorentz force. Actually, we use reluctant force to build up the rotation. So this rotor will be simple, reliable, have no carbon brushes. So that's why I'm making this motor will be really reliable and easy to use too. The configuration, the construction also straightforward. And so the principle here will be we generate the force by switching the stator coil to pull the rotor pole. So that means if the rotor in this position, when we turn on this one, you just pull the rotor to have the alignment to produce this kind of the reluctant force. So the principle here is not using Lorentz force, but using reluctant force. So this is another diagram, another configuration for even motor. But you can see that this is slightly special, right? What's special is that we put the winding in the center, you see? And then you see the salient poles will be on the outer rim. Anybody can tell me what kind of motor would that, the application, would that be? You see, before we put the winding in the stator, but now then we put the winding in the inner configuration. Outer configuration is no winding. So probably in this case, when we energize this winding, this outer rim will try to rotate. Yeah. We'll try to rotate to align the magnetic flux. So the rotation will be outer rim. So outer rim rotate. Yeah, so it's different from the inner shaft to rotate. Anybody can tell me what kind of application would that be? More look like to be?
Cleaning robot.
What kind of robot? Say again?
Cleaning robot.
Cleaning robot. You think cleaning robot, the rotation will be outside rather than inside? It can be. I mean, actually, this motor, I use them for electric vehicle, the in-wheel motor. In-wheel motor. So that's a wheel. This is the rubber wheel. So the motor rotate directly at the rubber side. So in this case, it's so-called the in-wheel motor. In-wheel motor is one of the famous development for four-wheel drive. We can able to implement this kind of motor in each of the wheel. So the motor outer rim will rotate directly without using gearbox. So that's one of the good development. So we can able to use this system for the four-wheel drive. That will be 100% four-wheel drive. At the moment, most of four-wheel drive vehicles, they are not 100% four-wheel drive. They use central engine to control four-wheel using some differential gear or so. So that means they're not 100% four-wheel drive. For this one, if you use this motor, then the rotation can be from 0 to 100% in this manner. So that's to say, you can see that this kind of SR motor, we can do it like inner rotor or outer rotor too. The configuration are quite simple and straightforward. So the point here is we have salient pole. So that means both the rotor and stator, we do have salient pole here. And the rotor, the rotation part have a no winding here, no winding. So if no winding, that is to say the rotating part have a really light inertia, really simple configuration. Once we got winding, the configuration will be really large or quite stiff, so you're not able to produce really light rotor. So if the configuration, the rotating part are really simple structure without too much component built in, then the whole rotor will be light, have low inertia, can have high rotating speed. So once the stator energized, then create a magnetic flux in between the two stator, pass through the rotor. Then in this case, you can able to attract the nearest rotor pole to this excitation. So which one is nearest, they will try to move it by using reluctant force to have the alignment here to produce the rotation. So this is how the principle behind how the rotor can be rotated in such a way. So the quick principle here, try to minimize the magnetic air gap. You can see that here, the magnetic air gap is so large, but this magnetic air gap will be so little. So that's how we try to do that. So what happened here, when we energize here, then become alignment. Next, we stop this current and energize the next one. Then this will therefore rotate into this direction to continue the reluctance circuitry. So later on, we can see the sequential manner, how we energize the winding, how the rotation of the rotor look like. So the shown operation is different. So here we'll show you different kind of the structure. So let's see in here, there's a 6, 4. So this is 4 in here. So this is 6, right? And then you can see that what happened here, he may energize this kind of the winding. Then you will have first an alignment, right? And then next, if we energize this winding, then this will try to rotate in this part to have this first alignment. And so on, when you energize this winding, next energize this winding, then this will therefore continue to rotate. Yeah, later on, got better diagram to show you. So that means you can see that each of the winding are highly independent from each other. So that's why you are able to create this kind of the excitation. So this is another X6. Then we got 8 of here. So for instance, when we energize, so these two, when we energize it, then it is first alignment, right? So next, if we energize these two, then this will rotate to here until these two have the alignment and so on. Okay. So you can see that the number of the stator and rotor should be different. For these two examples, they are different by 2. They cannot be equal. If equal, they always lock up, cannot rotate at all. So that's one of the issues. So usually they are different. So these are two famous arrangements, 6-4 and X6 SRM. So usually the first figure, the first number relate to the stator, second one relate to the rotor. So let's see this configuration. What can you tell me about what kind of the configuration it is? Is it still 10-8 or 8-10 or 10-10? Is it 8-10, 10-8 or 8-8 or 10-10? What kind of the configuration it is?
10-10.
Yeah, it's 8-10. Yeah, it's 8-10. So you can see that now we got less stator compared to rotor. And the arrangement will be also slightly different. But remember, always stator and rotor are different. Of course, most of the common case will be we got more stator than rotor. But it's also possible we got more rotor than stator too. That will be possible. We need to check. For instance, now it's first alignment, right? And the next thing to do that, then if we stop this current, then we energize this current, then this one will therefore rotate to here to have this alignment, right? And then let's energize this one. Then of course these two will rotate to here, this fractional alignment. So we got very different way to arrange. So the beauty here is we are able to have different number of stator and rotor to create a different kind of the rotating pitch angle. And then we are able to energize them in such a way. One thing we notice that will be, firstly, from this observation, all the stator winding, they're independent from each other. We do it one by one. We don't energize them together. We don't have to, but we still can, depend on number of phases. Later on, we'll teach you in next few slides, there were many different kind of operation. Firstly, for this simple configuration, like the 6X and X4 or X6, like these two, all the stator are highly independent from each other. When we energize one stator winding, the other are disconnected. So that is to say each one contribute their own torque. So like we have this torque in here, and then we stop this current, no torque, and then we energize this one, they have the torque from here. So the torque will come from each set of the winding in a kind of the independent manner. So what's the advantage of this? That means they are independent. They more look like in here, you got 3 parallel sections produce the torque. That's called 4 parallel sections to produce the torque. Each one will be independent. That is so-called the fault tolerance. Because in case one phase is broken, we still have another phase to make up. Although the total number of torque may be decreased, but however, we can still able to make sure the motor continue to work until the next maintenance. So that's a wonderful of this motor, highly fault tolerance, highly independent from each other. You see, other industrial motor, if one phase broken, impossible it can work. This motor as well, one armature winding broken, I don't think it can work. So, but this motor, this kind of capability. So remember, number of stator pole and motor pole are different. They use it different by 2, but of course can be other ratio. So you need your careful mind to check the geometry, to do some drawing to see what's the best combination. Yeah, for example, like this X6, could X4 be working? No, probably not, because there would be some kind of symmetrical alignment. We try to make them let the always alignment can only appear for one set of the face. And one set of face align, the other face should not align. So in this case, we don't have the lock up. Lock, that means they stay in that magnetic position, cannot rotate. So magnetic lock up would be when the stator and motor pole have same number of number. So once we rotate at that position, they will align at the same time. If all the stator and motor pole align at the same time, then we have no way we can get out from there. Later on, we can show you under the alignment, the rotor have no torque at all. The torque cannot be generated right at the alignment position. So that's why once we stay in alignment position, the rotor cannot rotate. You can see that when you initially start the rotor, you never can sure where the position of the rotor is. It can be okay, cannot be okay. You can see that if you are doing in this way, like in this rotor, if initially all of them are symmetrically aligned, so like this alignment, so in this position, have no torque generated. So if we don't have this one, then the motor never can be rotated. So that means, however, for this motor, then we do have this alignment here. So this can generate torque. This can also generate torque. So if this phase doesn't work, I can energize other phase, can start the motor rotation. So this kind of motor, we can ensure that we can able to start the motor. But if the motor always symmetrical or aligned in all the phases, in some condition, the motor cannot start at all. So that's the issue. So that's why we need the state of zero torque may happen due to the 100% alignment or total full alignment. Then we cannot do anything. So in this case, the rotor will get stuck in that particular position and no tendency to move at all. That's the thing we don't quite like. So because of this one, we need to have a different current for stator and motor current. So when they're different, then there will be a good chance that not all the poles, at least a few poles, will not alignment. If no alignment, then we are able to start the motor. Because when no alignment, we are torque. Alignment, no torque. So that's the way to do that. So that's why we do this so-called magnetic imbalance in any one of the salient pole to do that. So once we got this unbalance, we do have able to have some attraction. So that's one of the things to do that. So the controller will try to energize all the different phases to make sure the rotor can rotate. Because all the driver will energize each of phase in certain sequence. If this phase does not start, next phase and so on, there must be a phase can start the rotor. The time when we change the phase only takes a few milliseconds. You may delay the starting from a few milliseconds, but doesn't matter. So for instance, you can see that in this illustration show you if all the phase like this 4-4, all the phase are aligned in such a way. So for instance, this is something like that, right? Not very good drawing. So this 4-4, right? They all align in such a way. Because in this position have no torque. So the motor can never rotate. Of course, you never know. If the start position is this, you cannot start the motor. Of course, if the motor is being like this, then of course you can still start the rotor. But if they're symmetrically 45 angle degree, the torque of this side and that side are also equal, then the rotor can also not able to start. So that's why this motor, for fully alignment like this, we don't like that, cannot start the rotor. So that's why if the number of poles and in the stator and rotor are different, then you can see that this is alignment, all these are unaligned. Then this will have the torque. So eventually we should able to start the rotor. So that's simple configuration to show you one of the geometrical design for the rotor. So that's I like this kind of the arrangement so well because I can design the arrangement for the stator and rotor, design the salient pole, and design all this combination. So that's why it become really interesting. Up to this point, do you have any questions? Have you ever learned SR motor in the past? How about Xiaodong? Have you learned that? Sorry? Okay. It's quite interesting. Anyway, so this diagram shows the configuration, how to rotate. I think it's very straightforward to see that. If you do have first alignment here, then this position have no torque. And then now we disconnect it, and then we start to connect it. For example, connect it to a battery or whatever. Then we magnetic flux go through them. Then therefore, this will start to rotate here. Then we have this flux alignment, right? And the next, if I can energize this set of winding, then we also have flux alignment here, so it pass through here. Then you start to rotation. So that's the way we are able to rotate the rotor. So you can see that the concepts are quite simple and straightforward. You can actually visualize them by using geometrical principle to understand the rotation. But for induction motor, probably you never can understand how you will rotate. Although in the lecture I say, oh, rotating magnetic flux, we interact with Lorentz force, but of course you still don't quite understand where the force comes from. But here you really can able to visualize, can feel how the force comes from between the stator and rotor. So that's why it's more interesting to me too. So this diagram to show you step by step how we're able to rotate the rotor. So we're going to energize. So we firstly energize this first, and then we energize this, and then we energize this 3, and then we energize this number 4 in that sequential manner and continuously to energize them. Can you tell me what the rotation without looking at my bullet point? So you see, I do it in this, the stator, I do it in this clockwise manner. But do you observe that rotation for the rotor are clockwise or anti-clockwise? Spend 1 minute to have look what it look like, clockwise or anti-clockwise.
Clockwise.
Now the stator is clockwise. How about rotor?
Clockwise.
Xiaodong, could you tell me your observation?
I don't understand the stators.
Now, I energize this stator, this set of the stator, right? Then you can see that this a little bit spike here mean the reluctant force try to attract these two, right? And then start to move, right? To move them to alignment. After it done alignment, I energize this set of winding. And then there will be reluctant force to rotate it, right? And so on. So the question is, you can see that the phase sequence will be moving in such a way for the stator, outside stator. But the inner rotor, what is the rotation direction? Anti-clockwise. So firstly, you do that.
Yes.
And then this will become, you see this, try to have alignment here. So this need to go this way. Now going this way.
This will go, okay.
And then when we energize this one need to catch up. So this need to rotate to align this. Okay. Force it to align in such a way.
Okay.
And then next, then energize this one. This will force it to align. So you need to continue to rotate in such a way. So that's why the phase sequence for between stator are opposite to each other. When the rotor in clockwise, the rotor will be anti-clockwise, and vice versa. So that's also one important point for SR motor. We can use this kind of phase sequence to control the rotor direction to forward or reverse. Okay, so that's the concept. Very easy to know because in the Lorentz force, you may need to use your three finger to determine the motor direction, but now you only use observation. You can see the rotor rotational direction. Okay, so here will be different combination. Of course, there are a few really common combination. Of course, this one do have some problem because the way to start the rotor will be problematic. We're not able to start the motor really well, but I think the other are quite okay. So this, you can also see the configuration. So this, you can see the lamination here. So all this motor, we do need to look into the lamination. So you see all the winding is here. So that means the winding is this direction. So we can see the magnetic flux will go through in this way, right? So the magnetic flux will go through in this way. Then that means the eddy current, if you use your finger, you can see the eddy current tend to go this way. So that's why the lamination must be put in such a way to stop the eddy current. If you're not quite sure about the eddy current angle, you go home to check it. But anyway, when we have winding in such a way, the winding in this, then the B field will go this way. And eddy current will go this way. So that means you pass through the lamination. So that's why we need to have lamination in this direction to stop the eddy current. Okay, so that's how our configuration for the lamination look like. We do need to have lamination for both stator and rotor. So all the lamination will be in such a way anyway. All right.
Can you please repeat this?
You mean eddy current? Okay, I can repeat now. Do you see the winding in here? The winding will be in here.
Yeah.
So that means the current going this way, the magnetic flux will go. So the magnetic flux will go through in this direction, in the radical direction. The magnetic flux, because winding like this, will go to radical direction. Radical direction means along the radius. So here the D field goes for radical direction like that, and the eddy current will therefore going out like this. Eddy current will flow through this way, go in and go out. Yeah. Then if the eddy current generated by the B field will go in this way, then the eddy current try to penetrate from here to there. So that means our lamination should put in this direction to stop the eddy current flow through. This requires kind of the lens law or visualization where the eddy current go through. So basically, that's how I just explained to you why we put the lamination in such a manner. Not in this manner, but it will be in this manner. Because the eddy current will go through here. All the lamination will try to stop the eddy current to pass through all the layer of the lamination. Of course, if you can use finite element to examine that, but of course for basic design, then we use our lens law to examine how the lamination should be. So the eddy current actually pass through all the lamination. So this is another configuration to show you 12-8 SR motor look like. So anyway, so this tool will be a combination, must not be equal. So usually it will be even number. You can imagine it's equivalent to 6-4 motor, but we just double them. So in this case, it just look like we putting two 6-4 motor together. Each time we energize two set of the winding. So that means in here we can have two set of winding. So you see 6-4 motor are more look like three phase, right? So here will be this one. We can also make it three phase, but become three phase. Each time we energize two set of the winding. Mhm. So again, you can see that we not quite sure you understand about the sailing poles. So they all are sailing poles. So of course, most of the motor are using the sailing poles. The configuration, this one also simple because this is the form. Do you see the white thing here? This is the bobbin. So we use a bobbin here. We first use bobbin to do the winding, and then we insert this bobbin, insert into here. So configuration is quite simple. We just have a kind of geometry like this. The geometry will be just like this geometry. We can make up this geometry. And then later on the bobbin, after winding, we can insert into here. So that's how we configure the assembly. And after that, we can insert this rotor into the shaft position. So that's why you can see that all the configurations are quite simple. And also this one is also low inertia and also quite light. We have no winding, no PM there. So that's why I stress that the production for SR motor are relatively simple because we only have a set of winding in the stator. The rotor, you just have all the lamination here. And so become quite, and all the winding can be pre-winded beforehand and then push them into teeth of the stator. That means it's the sailing poles. So the inductance is one of the important elements to determine the characteristic for the motor. One thing will be alignment or disalignment. When the stator and rotor, they align, so that means in this here, like in here, when this is called alignment, and the inductance in this part between them will be the highest inductance. Fair enough, because air gap is the lowest. And then when they align, the inductance will be lowest. So that means you can see that in here, 100% an alignment, you can see that probably in here, in this part, right? In this part, they are 100% not aligned. So this part will not aligned, the inductance will be lowest. Then the inductance, actually we found that they are linearly proportional to rotor position, like in this curve. So later on, we can see that when we calculate the torque actually are highly related to this inductance tangent, the curve here. So we're going to prove that the torque actually not only relate to the current, but also relate to the inductance profile. So I show you the next slide. So also that, firstly, we got the first linkage. The first linkage, of course, the first linkage equal to the inductance and current, of course, equal to N5, amount of first pass through that. In here, we don't have the first parameter, but we do know that it relates to the first linkage and current. But the inductance actually is not inductance here, not fixed. Inductance here is related to the current and highly related to current. So that's why I can see that although highly related to the angle, when we rotate, alignment, disalignment affect the total reluctance because related to air gap. So that's why I can see that the energy stored in magnetic circuitry, by definition, is the lambda delta I is the energy storage in the first linkage. And then we can therefore putting that into here, then we can divide into equal half Li squared. That is similar to the energy storage in the inductor. So in the energy stored in the inductor also equal half Li squared. But that's different. Inductor, this will be fixed. But this inductor will vary with the rotor angle. And also, not only that, the inductance also change with current. In many papers, they say it not change with current, but because magnetization, the inductance do change slightly with the current. Just like transformer or any winding, the inductance may vary slightly with the current too. But usually, you can assume that independent of current, but highly depend on the rotor angle. So that's so-called the cold energy. Cold energy is the variable energy, the energy stored in the inductive component of the winding. We define them as cold energy, not the real energy. So more interestingly, to look at the characteristic for the cold energy. So there's a really famous diagram for the cold energy. So when we plot the first linkage with the current, then we can see that the first linkage actually is nonlinear curve and also relate to magnetic saturation. So probably this will be getting more saturated. So but probably beginning the curve more linear and then relate to the saturation. So the cold energy is not a real energy, you can see that, but it's a variable energy we stored inside the inductor here. And this, we usually, for many textbooks, they use the term called WF dash. Dash means they're reactive. They're not the real physical, real energy stored. Then we also have the magnetic energy stored in the magnetic circuitry here. Then we call it WF. But key thing here, we look at the variable energy in the inductor to see what it is. So we can actually, using the integration, many textbooks, they use integration. For example, they try to measure this energy with delta lambda. They have this delta lambda, which can use this integration to integrate the whole thing here, here. And then for the cold energy will be this one. They try to use this kind of the delta I, and then we can measure the cold energy here. Then we observe that the cold energy is something special. What's the cold energy? It's difficult to explain you by using this diagram, but what I can tell you will be cold energy more look like magnetic potential that's stored during the motion. What you mean here will be is how the magnetic system try to move to lower stage. You see all the energy, they try to move from the high stage of energy to lower stage. So that means, for example, like a spring, when you stretch out, then you can store the energy there. Then you try to return to low energy position. So that means when stretch is store energy, when you stretch them, then the string has potential, try to return to its original position. Then SR motor is the same. They have inductor. So when they align, that will be high inductance. But when it away from the alignment, it try to look like stretch the inductance into another unaligned state to store the energy at that position. And then you try to return its original alignment position, similar to the string. Spring will pull it, but for our SR motor, we move it away from alignment, but the magnetic force try to return it back. So that's how the cold energy being measured. So the correlation between them will be, if a single phase being energized, it tries to look like restricting the magnetic string between the stator and motor. The stator and motor, between them, you see, we have stator. So between them, more look like there's a string between them. If they align, we got our best stable position. When we pull it away from each other, so we just stretch the stator and the rotor to a lot more elongation and they store more energy. So that means our stretched string will have a higher potential energy, create a strong pulling force. So similar to our cold energy will appear in here, that will create a large tension in here to store more energy, try to pull it back into its alignment. So that's how I can imagine, because cold energy is difficult to explain to you, but what I can see here will be trying to relate this phenomenon with so-called the spring, more look like a magnetic spring to do that. So energy. So this kind of energy will therefore convert into torque or the force. So in the work done we have here, you see the work done equal to torque multiplied by the angle, which we also quite low. The torque equal to force times the distance. So these two are related to each other anyway. So If our motor move a small position, then we have to change into the co-energy. Once we move the spring, then we have co-energy change. So the way we change the co-energy with the angle, this will become our torque. So that's how we can see that. That's similar to the correlation when we have the work done mean the torque multiplied by the angle. This mean this is the co-energy, that's a change in the co-energy. So by this similarity, we can say that the torque actually equal to the change in the co-energy related to torque. We're just putting this in here. That's how we can get the physical meaning. Change of the co-energy equal to torque. Or, for example, like in Newton law, change the energy storage also equal to the force. But here, we are not using linear, we use rotational, so change of energy with respect to the angle become our torque. So now then we use this definition to look into the torque equation, which is more important here. So the energy stored into that magnetic energy storage, half Li squared. The L is related to the inductance. The inductance here is related to the angle. All right. So now then, to get the torque, we differentiate the energy. We use partial differentiation. Why is that? Because the inductance actually could be related to the current and the angle. At the moment, we assume the angle is, the current is constant. We get down to this equation. So this equation gives us a lot of the observation. It's really important equation for the whole chapter. So the torque actually for reluctance motor are proportional to I squared. Can you tell me what's meaning for I squared? It's proportional to current, we know that. All the torque are related to current, but now it's not proportional to I, but proportional to I squared.
Because of two sides?
Yeah, we had a square here. What does that mean?
Because we have one up, one down, two windings, that's all.
Not only this one. What you observe will be how we generate the torque. But in here, you see when we did misalignment, we create a force. But of course, the winding also need to have the current. Then we can therefore, we need to inject current into the winding to create the torque. If it's just misalignment, there's no force or no torque. We need to inject with the current. So that means we need the change of
Inject
inductance
and produce.
with the two items in order to produce the torque. So we need the current inside the winding. But I observe that the current here is I squared, not I. Why is that? Or we can say, what is the observation? You can see when we see the torque are proportional I squared. That means the torque independent of current direction. No matter injecting current or remove the current from the winding, the torque is same direction or rotation. You see in the DC motor, IA change the torque direction. In DC motor, torque is proportional to KIA, right? So we can change the direction of current to change the torque direction. But in here, because of I squared, no matter you change the current into any direction, the torque is unchanged. So that one observation. The only one way we can change the direction is the L d theta, which is this angle. Yeah, that slope. When the slope is positive, we are so-called the torque will become positive. When the slope is negative, the torque will become negative. So that is to say we only can use dl d theta to change the torque direction. We cannot use the current. So the operation here will be different from other motor. So that means when the slope is positive, positive slope, then the torque become positive, and vice versa. So when it become positive or when it become negative, when the alignment try to approach the rotor, approach to the alignment, approach it, then we supposedly inductance will be increasing, right? Then that is positive torque. But when the rotor try to away from the alignment, it's decreasing the inductance. Then in this case, we have negative torque. So approaching is positive, away from the alignment become negative. So that's something we need to be really careful, the operation. So this operation affect how we control the motor too. Up to this point, do you have any question? Do you understand what I'm talking about approaching? So that is to say, if you go back to the previous curve, you see, yeah, when this approach here, the torque here will be positive. Yeah. But when the motor is already away from here, then the force between them will become negative. So that's why approach and away from the alignment will determine the force or the torque direction. So that's something important for us to control. And then in here, during alignment position, there won't be any torque because there's no variation of nothing. So you see here is flat, no variation. So even though in the alignment here, if the rotor have a larger size than the stator, we also have flat point in here. So at that point, there's a no torque. No torque. So that's something we need to. So that means how to control the rotor will be important. The thing is, this is negative torque, this is positive torque, right? So that means if we have a current, the current we need to put on here. In here, we need to have no current. If no current, we have no torque. So that means to have a continued rotation of the rotor, we energize this winding with this current IA, right? Only when the slope is positive. Once it passes through this point, we just stop the current on and off. So that's the way we control the rotor winding, not control the stator winding. So that is to say, we will turn on, and this will be off. So that is to say, we really need to monitor the position of rotor with a sensor for the rotor position to determine when to turn on and when to turn off the transistor. So in the little field page, you can see that we got different kind of the driving circuitry. Which one? So we energize one by one, but how to turn on these two transistors depend on the position of the rotor. So that's why this kind of the SR motor, we need really good observation or good sensor for the rotor position to do the job. All right. I think it's 5:45. We stop here. I think it's really interesting motor, easy to understand. Operation is quite complicated, not complicated. We need a lot of the control. So that's why I make this motor not easy to control in the 50 years ago, but now become so simple, really easy to do that. So I will continue after the Thanksgiving. We have no lecture on Thursday, right? We'll come back next week. So I will start to post the homework 5 there. Then we can start to do the homework 5. The due date for homework 5 will be after maybe 2 to 3 weeks. Okay, thanks again. Have a nice holiday. And I will see you again after the Thanksgiving then.